Now we're going to look at some sort of exotic functions associated in college algebra with finding the domain, the set of all input values. Now this was based on a lecture. So we're going over some homework questions, going over the odds here. Now I want to remind people that we can't divide by 0. You see, we have a rational function, and what we have to find, like we did in class, is where the denominator equals 0. So we start by setting, since I said earlier that if you have a rational function, then we could never have that denominator equal to 0, because that would give us an undefined rational or an undefined fraction. This will be undefined. So by setting that denominator equal to 0, we get x squared equal to 0 now. And at this point, we simply solve for x. Now, x squared equals 0, we can think of as a couple of things. We can say that implies that x is 0, because the only way we can multiply two numbers together and have it be 0 is if that number was 0, meaning 0 squared equals 0. So here's our solution here for the equation. However, when we're talking about the domain by definition was a set of all input values. And so in the context here where we have a rational function, using 0 as an input will give us an undefined fraction, right? If you recall, if I plug 0 in here for x, we get 4 over, let's keep that in red, 4 over 0 squared, which will be 4 over 0, which is undefined. So we're using here this approach. We want to actually find where the denominator equals 0, because we don't want it to be 0. That's where the fraction will be undefined. So we throw out this value from our domain. This is the only location of our rock. So our domain here in set notation is the set of all x such that x could not be the value 0. So this was the premise here that we used in class for finding the domain of these functions. We simply set the denominator equal to 0, find where the rocks were, the values of x that will give our fraction an undefined status, and at that point we throw that out. So this is a rock, this is what leaves, and so this is how we answer that first homework question. And this is going to be a theme here for all your homework questions. So these functions that we gave you in this exercise were all special. They're all rational or rational-like, or I shouldn't say all, some. And we looked at the other special situation, which was the square root functions. And we'll see those too. So I have 1 over x squared minus 9 for question number 3. Again, a rational function. We set this denominator equal to 0 again, just like we did in the first question. Now when I set that denominator equal to 0, we have to solve that equation for x. So we have x squared minus 9 equals 0. We'll have to solve for x. This is going to give me the location of our rocks, the values we throw out, the values that x can't be, the values that are not in the domain. So we have a couple of ways of solving this. We can factor. We can use the zero product rule as we factor. Or we can actually use techniques in intermediate algebra, which is to add 9 here to both sides. And we'll now have x squared is 9 because this is a quadratic, which means x will be plus or minus square root of 9. And we know the square root of 9 here is the value 3. So our answer here is going to be x is plus or minus 3, and this is the location of our rocks. We can't have x be these values here. So again, notice if we plug in a positive 3, we get 1 over 3 squared minus 9, which is 1 over 9 minus 9, or simply 1 over 0. That's an undefined rational. So x can't be that value 3. If we plug a negative 3, we'll have negative 3 squared. And that again is going to give you 9. And we have the same situation. So this can't be plus or minus 3. This is the location of our rocks. So in set notation, the domain will be the set of all real numbers x such that x could not be plus or minus 3. So when you have a rational function, simply set the denominator equal to 0 and solve for x. Number 5. My function here is 1 over 2x squared minus 8. Another rational function. So we'll set the denominator equal to 0 again, so we can find the location of our rocks. And this too can be solved by using the square root formula, or we can solve this by factoring. So if we want to take a different approach, let's factor here. And what we mean by factor, we can take out the greatest common factor. Now the greatest common factor here is going to be 2, and my quotient is x squared minus 4. So we're going to solve this quadratic equation by factoring. And so you notice now what you're left with here to factor this quotient here is a difference of perfect squares. So we factor this as x plus 2 times x minus 2. And we could use the zero product rule again here. And by the zero product rule, what this means is two things. This means the first term here. Let's change colors here. That means x plus 2 is 0. So we can write it here. This also means x minus 2 is 0. So people may wonder, how come I'm not using the fact that 2 is multiplied to these terms and we get 0? Well, 2 could never change our answer here to be 0. The only variables we have in our equation here is here and here. Some students, what they like to do is divide both sides here by 2 if it makes them feel better. You get cancellation, and you still get this x plus 2 here times x minus 2 equals 0, which is the same process. So I could ignore the fact that I have a number here that's certainly not 0. That's not making our product 0. But the other two terms are. So I can use a zero product rule now if I choose, and either way will work. So we subtract 2 to finish the process. We add 2 to both sides here, and we get x is negative 2. We get x is positive 2. So again, these are the values I have to throw out. These are my rocks. These are the values that x can't be. So my domain here again will be the set of all real numbers x such that x cannot be plus or minus 2. And you're done here. Number 7. F of x. 1 over x squared plus 36 here. So again, in this question here, since it's rational, fraction, again, we set that denominator equal to 0 again. And we solve for x. And at this point, we're going to notice here a couple of things. There's a couple of ways that we've seen for how we can solve this quadratic equation. And again, remember, this is a quadratic because we have the highest power here, b2. And one method was that I subtracted 36 from both sides. And in that method, I get x squared is minus 36. Now by the square root formula, what this gives us is x going to be plus or minus the square root of 36, which means x is plus or minus 6i, because the square root of a negative 36 here is actually 6i. It's complex, it's imaginary. So our solutions here for this equation here, the rocks, are complex numbers. Now remember, we're only considering real numbers. So when you get complex numbers, if the context is real numbers, what you can say is simply is that there's no real solution here. Meaning even though you solved for x right here, and you got x is plus or minus 36i, these are not real solutions, so we don't even consider these. Okay? And so that would mean here that our domain, in the context of real numbers, we can say that the domain here is really all real numbers because there's no rocks here. So x squared plus 36 will never be 0, and this is what this means. So let's go back. This denominator could never be 0. And in fact, this denominator will always be positive here. Because it doesn't matter what value we put for x, the second we square it and add a positive number, squaring a positive and a negative will always make that positive. Adding to a positive number makes it positive. So this arithmetic will always be greater than 0, positive. Now, you may have said, or you may have noticed that going back to solving this quadratic, you may have said, what happens if we factor? Or what happens if we try to factor? Well, you can't factor here because this is not factorable. So the sum x squared plus 36 is not factorable. So let's remember that. And when it's not factorable, you have the same conclusion here, that there will be simply no real solution, which means your domain is a set of all real numbers. So this is number 7. Number 9. Your function here is 1 over x squared plus 8x plus 15. Your denominator here can't be 0. So we set this equal to 0, and we want to solve for x. We want to find the values here that we have to throw out. We want to find the rocks. Now, there's various ways to solve a quadratic. We've seen factoring and using the zero product rule. We have seen using the quadratic formula. We have seen complete the square. So you have various techniques for solving a quadratic. If you can factor, I highly recommend you factor. I think it's the fastest and the shortest way to go. And so I'm not going to review how to factor here necessarily for these questions here because we have a bunch of resources on factoring. I'm just going to say review those resources on how to factor a trinomial here or use the chicken soup recipe. I might try this technique again to remind you guys at first how we can factor, but I certainly won't go through every question with this technique. But let me remind you here. Some people really prefer this high school method where the product has to be 15 and the sum has to be 8. So we first have to find this number is the product, which is what we put here. And the b value is your sum. We have put that down there, and we need two numbers multiplied together that satisfy those two constraints. And you'll find that the numbers are going to be positive 3 and positive 5. So we know that 3 times 5 is 15, and 3 plus 5 is 8. So these are the numbers here. These are the numbers that we place in these key positions. Sorry. So there you go. You're going to place those numbers there. Okay, so this goes right here, and this goes over here. And so now you factored. So let's get rid of some of this, or at least rewrite it. And so now when we use the zero product rule, we'll have x plus 3 is 0, x plus 5 is 0, so I could subtract my 3, subtract my 5, and I get x is negative 3. We get x is negative 5. Now, this is the location of our rocks. These are the values of x that will make our fraction undefined. They'll make this 1 over 0. And that's what we can't have. So just throw them out. So your domain will be set of all real numbers x such that x could not be negative 3 and x could not be negative 5. This is the location of your rocks here. We throw those values out. So your domain will work for any other number but these values. It's number 9. Number 11. 1 over okay. So again, I'll remind you that we have a rational function. We set the denominator equal to 0. And we solve for x. So x squared plus 2x minus 8 is 0. Now again, we factor. So if you like, review your factoring. Remember, the product has to be negative 8, and the sum has to be positive 2. Because this number goes here, and this positive 2 goes here. So we need two numbers multiplied together. That is negative 8, and when added is positive 2. So let's think about this. Negative 4 times positive 2 or positive 4 times negative 2? I think positive 4 times negative 2. Let's double check. 4 times negative 2 is negative 8. 4 plus negative 2 is positive 2. So these are the numbers that we can use to factor our quadratic here. Okay, we could put it down here. X equals 0. And so the first number is going to be positive 4, and the second is negative 2. Remember, these numbers here go all the way down there. This number goes over here. So by the zero product rule now, we'll get the following. X plus 4 equals 0. We get x minus 2 equals 0. Subtract your 4 from both sides, add your 2 to both sides, and we'll get x is negative 4 and x is positive 2. This is the location of your rocks. So your domain here will be set of all real numbers x such that x could not be negative 4 and x could not be positive 2. Number 13. 10 over x cubed minus 2x squared minus 35x. Again, we set our denominator equal to 0 to find the location of our rocks. X cubed minus 2x squared minus 35x equals 0. And again, at this point, we don't have a quadratic. We have the highest power here not being 2. We have the highest power being 3. Again, at this point, we're going to factor. And what we mean by factor, we mean factor out the greatest common factor. So the greatest common factor of x cubed, 2x squared, and 35x will be x, and now I need my quotient, x squared minus 2x minus 35, and this equals 0. So at this point, we're going to need to factor this quadratic here. And so you can go through your technique again, where the product has to be negative 35, and your sum has to be negative 2. So we need two numbers that satisfy this criteria. And it looks like it's going to be negative 7 times positive 5, because negative 7 times positive 5 is negative 35, but negative 7 plus 5 is negative 2. So when we continue to factor, we'll have x times x minus 7 times x plus 5, and this equals 0. Okay, we simply use those numbers again found as that pair, and they go here. Okay. Now, you're going to notice something about this. This is the first time we see 1, 2, we see 3 terms multiplied together, and that equals 0. So we can again generalize by putting all 3 terms equal to 0. X is 0. X minus 7 is 0. X plus 5 is 0. Now, this first term is already equal to 0. But I'm going to have to add 7 to both sides here, and I'll get x is positive 7. Subtract 5 from both sides, and I'll get x is negative 5. This is the location of our rocks. These are the values of x that we can't use as input values for this function. So our domain will be the set of all real numbers x again, such that x can't be 0, x can't be 7, and we'll put down here x can't be negative 5. Because again, these values of x will give us 10 over 0, which is undefined. Number 15. Seven over x cubed minus 1. Again, we set this denominator equal to 0. So you have x cubed minus 1 is 0. And again, when you factor, this is a difference of perfect cubes, because 1 can be thought of as 1 cube. So we're going to factor that denominator. And by our difference of perfect cube formula, let's remember that we get x, 1, x squared, 1 squared, 1 times x, which is x. This is minus, this is opposite, and this is always plus. So 1 squared is 1, so I can simply replace that with 1. This will equal 0. So we did factor. It's not a quadratic, it's a difference of perfect cubes. And I want to remind people that when you factor a difference of perfect cubes, when you're trying to solve a equation here that it's equal to 0, by the zero product rule, we can put both terms equal to 0. X minus 1 is 0. X squared plus x plus 1 is 0. And I want to remind people that this second term here, which is what we put down here, this is not factorable always. So let's kind of write that clearly if we can. So this portion, again, this is not factorable. It'll give you complex answers, complex solutions here. So our context here is real numbers. So what that means is this portion isn't going to be useful for us. We can ignore it because we know it's not factorable. It's going to give us complex numbers. We just have to solve the first equation, which is done very easily. We now get x is 1. So your domain here is going to be the set of all real numbers x such that x could not be the value 1. So this here is thrown out. If we use 1 as an input, we'll get 7 over 0 again, which is undefined. And that's what we're trying to avoid, dividing by 0. So here's our answer. This is the domain. Number 17, we have a function here, 7 over x to the 4th power minus 8x. So at this point again, we set the denominator equal to 0. And we solve for x. So we're going to factor here. So when we mean by factor, we have to factor out the greatest common factor. So the greatest common factor of the two terms here of x to the 4th and 8x is simply x. We're now left with x cubed minus 8 equal to 0 as a quotient. So the first term is our greatest common factor. Now the second term here, we're going to have to factor this. So if you notice here, factoring x cubed minus 8, that's x cubed minus 2 cubed here. We have a difference of perfect cubes again. This could be factored as the following. X and 2, x squared, 2x, 2 squared. Difference, plus, and plus. So we use the difference of perfect cube formula. And let's remember that 2 squared here is going to be the value 4. So altogether, we have x minus 2, x squared plus 2x, plus 4, and then that equals 0 here. And so by the zero product rule, again, we have one term, second term, and a third term equal to 0. Let me remind you, like the prior example, this term is not factorable. And so that's going to be an issue, or that's going to be of importance for us when we use the zero product rule. Because we'll end up putting every one of these terms equal to 0 in an attempt to solve for 0. And since the last term is not factorable, we'll get complex solutions here. So this last term isn't factorable. This is not going to be of useful information for us because our context, again, is real numbers. So all I have to do to solve is add 2 to the second equation to get x is 2. We already have x is 0 here. The third criteria, or the third quadratic there, is not factorable, gives us complex solutions, so that means we're done. So our rocks are at 0 and 2. So when we say, what's the domain, the set of all input values, it's going to be the set of all real numbers x such that x could not be 0 and x could not be the number 2. So here you go. That's number 17. Number 19. Our function here is 12 over 3x squared minus 7x minus 20. Again, we set the denominator equal to 0 again. So when we set that denominator equal to 0, 3x squared minus 7x minus 20 is 0. We have to solve this quadratic. Now, we can factor or use the quadratic formula or complete the square. I'm going to factor, and we're going to use that old high school technique, that X technique that people like to use when factoring. And it's slightly different here. What's a bit different is I need to multiply 3 and negative 20 first to get negative 60. And then I have my negative 7 here, so this goes down here. And this will still be my sum. So don't forget, when you have an a value here, this is my a value, and a is not 1, we do have to multiply that a with the c here. And we get the product being negative 60. This is still my b term, and so we're going to try to factor here using our X technique here. So I need two numbers multiplied together is negative 60, but when added is negative 7. So we can think of maybe 12 and 5, that's positive 60. And so we might want to try here negative 12 and positive 5, because negative times a positive is in fact negative. But negative 12 plus 5 is negative 7 here. So we can factor here. And we'll use the same process. Let's remember here, this is going to be x minus 12, x minus 7 equals 0. But let's be careful here with this, because a here is 3. So we have to divide this term by 3 and this term by 3. Now we notice 12 divided by 3 does give us a whole number. Remember, we always divide by the a value. So this will be x minus 4 here. However, when I take the 7 and divide by 3, I don't get a whole number. So we're going to put this 3 up here. So that gives us now a 3 here times that x minus 7, and then this will equal 0. So this is how we factor. And let's be careful here. We made a mistake. This number here is 5. So it's always good to go back and double check, which is what I did here, by using FOIL to make sure. If I use FOIL here, just by double checking, I should get this quadratic up here. And so it looks like we're good. We made another mistake here. So let's wake up here. Let's make sure the coffee's in us. This is plus, and this is plus here. So remember here, we use a positive 5 over here, positive 5. And we use a negative 12 over here, because this value is negative 12. Okay, it looks like we're good now. So it's always good to double check by using your FOIL here. And now we can apply our zero product rule, which means x minus 4 is 0, and or 3x plus 5 is 0 here. So I get two equations to solve. Add 4, we get x is positive 4. Subtract 5, 3x is negative 5. Divide by 3, and you get x is negative 5/3. So our final answer here is going to be as a domain, set of all real numbers x such that x could not be the value 4, or x could not be negative 5/3. And this is why we actually solve these quadratics here for x, because this gives us the location of our rocks. These values of x will give us 12 over 0, which again is undefined. So this is how we handle 19. The procedure is completely based on factoring, because we're finding where the denominator equals 0 and throwing those values of x out. Number 21, we get a function here to be 9 over 4x squared plus 23x minus 6. So we're going to set this denominator again equal to 0. So you have 4x squared plus 23x minus 6 is 0. We're going to try to solve this by factoring. You could use a quadratic formula if you like, but I think factoring is quicker. Notice the greatest common factor is 1, so we're just going to have to factor this by beef stew or by the high school technique again. So remember, we have a product here. We just take the numbers here. 4, negative 6, which gives you negative 24. The sum here is positive 23. So we'll need two numbers multiplied together, which is negative 24, but when added is positive 23. So if we think about this, negative 24 and 1, nope, negative 1 and positive 24. Let's double check. 24 times negative 1 is negative 24. 24 plus negative 1 is 23. So, okay. So these are going to be the numbers. So we'll put an x here, an x here. Let's make sure we bring the right signs here. Plus 24 minus 1. Let's make sure we even bring the right numbers this time. But because you have here an a value equal to 4 and it's not 1, we divide the numbers by 4 and we try to get a whole number. So with the first term, 24 over 4 does give us a 6. So we have x plus 6. However, 1 divided by 4 is not a whole number. So we're going to have to move that number, that 4 here, up in this position. So this is now a 4x here. Now don't forget that this is going to equal 0. So you can always double check again by FOIL. Just simply multiply mentally, not necessarily if you have to on paper. X times 4x is 4x squared. Positive 6 times negative 1 is negative 6. And 6 times 4x is 24x. And then x times negative 1 is minus x. So that's a 23x. So we did factor okay. Good. Now we use the zero product rule. Let's remember we set both of these terms. This product is going to equal 0. So we get x plus 6 is 0. We get 4x minus 1 is 0. Subtract that 6. We get x is negative 6. Add this 1, we get 4x is positive 1. Divide by 4, we'll get x equal to 1/4. So we get 1/4 and negative 6. This is where my product equals 0. So this is the location of my rocks. So I just have to, at this point, answer the question in set notation. We're going to say that the domain here is all real numbers x such that x could not be negative 6. X could not be positive 1/4. Here's my domain. This is 21. Number 23. My function here is the square root 16 minus x squared. This is a square root function here. Now let's recall, when we find the domain here for square root functions, what we talked about is we don't allow for the square root of a negative, meaning we are not going to consider complex or imaginary numbers here. This is only real values, real numbers. So what I need under the radical here in this question, 16 minus x squared, I need that to be actually greater than or equal to 0. So let's change the color here. I need 16 minus x squared. So whatever's under the radical, I simply set as an inequality. Not an equality, an inequality. That 16 minus x squared here must be greater than or equal to 0 here. So 16 minus x squared greater than or equal to 0. Now, this is where we use an important process known as sign analysis. Now, sign analysis, if you guys remember, we went over in class. We had lectures on sign analysis. There's a procedure here. So we're going to follow that procedure. And the first step in that procedure, if you guys remember here, is always to solve the equality. So you're going to try to find where this quadratic equals 0, because less than or equal means two things. So we're going to find first this less than or equal. We're going to find where the equality happens. And again, there's two ways to do this. You could notice that there's a difference of perfect squares here. So 4 plus x times 4 minus x equals 0 by the zero product rule. We say 4 plus x is 0, and we say 4 minus x is 0. So we can subtract 4 here from both sides, and we'll get x going to be negative 4 for 1. Here we can add x to both sides, and we get 4 equals x, or simply x is 4. So we actually solve two equations here. We solve the equality. This is where the quadratic, again, let's go back here. Equals 0. There's the equality version. What we have to do now is focus on where 16 minus x squared is strictly positive. So this is the point here behind sign analysis. We have to find where it's actually positive now. And so that procedure for finding where this is greater than or equal to 0 here, we go to this real number line here. Remember that procedure we did. We find where that product here equals 0, and we simply notate that it happens where the value of x is negative 4 and positive 4. Because we're looking at this particular product way up here. We're trying to know where 16 minus x squared is greater than or equal to 0. So we simply notated already where it equals 0. What we need now is some test points, because these zeros here partition our real number line again into 3 regions. So we have to test the sign of each region. So I need test points. I need a value to the left of negative 4. We'll say negative 5. Here's a test point. A value in region 2. We have 0 available. This is a test point. And a value to the right of 4, we can say 6 if we like. Here's our test point. We're going to test the sign of each region. So if you guys recall, you're going to go back to the factored form. That's the best form to use. 4 plus x times 4 minus x. So use the value here as a test point. The first test point we're going to use here, if you guys remember, is right here. We're going to test negative 4. Oops, sorry. We're going to use the value negative 5 here. Get so distracted by the art of this. So we're going to use negative 5. That's a test point. Okay, we labeled it test point. That's why I label it a T. So when I plug in negative 5 here and here, we get 4 minus 5, which is negative 1. And then we get 4 minus a negative 5. So I get negative 1, 4 plus 5, negative 1 times 9. Now I really don't need the value, I just need the sign. So I know that negative 1 times 9 is in fact negative 9, but I focus on the sign. Negative times a positive is a negative. So this is going to be a negative quadrant, or a negative region. That first region here is negative. So we're going to do the process here for every test point like we just did. But this time, we're going to test the value 0, which is really testing region 2. So when I plug in my 0 now, for x, I get 4 times 4, or a positive times a positive, which gives me a positive here. So region 2 is in fact positive. Let's test region 3. By testing region 3, we simply plug in, double check, we tested 0, we test 6 now. Those are our test points. Plug in 6. 4 plus 6 is 10. 4 minus 6 is negative 2. A positive times a negative, again, is negative. So this region is negative here. So this is our sign analysis. This is what we're looking for. So if we go back to the original question here, we set what's under our radical here, 16 minus 4x squared, right in here, we set that to be greater than or equal to 0. What that means is, where is it equal to 0 and where is it positive? Because numbers that are bigger than 0 are positive. So when you look at sign analysis, everything you need to know is right here. Meaning, region 2 is where the product there is positive, and we include the zeros because this is greater than or equal to 0. Greater than or equal to 0 here. So our final answer will be written graphically. I think that helps. You're going to shade everything right in here, including the negative 4 and the positive 4, because this is where your product is positive or equal to 0. So in terms of a real number line graph, you just reproduce the same graph you see above here. And you shade everything between negative 4 and positive 4. Just don't forget to use square brackets because we include where it equals 0. Now this is the graph. In terms of set notation, we have to describe the meaning of negative 4 to positive 4. So this is, remember this, x is going to be between these two values here. So we write negative 4, x, and 4. This is between, less than or equal, less than or equal. So this is the values of x that are between negative 4 and positive 4, including negative 4 and positive 4. This is our description. So for set notation, we say the set of all x such that these are the values that give us a positive or equal to 0. And then notice this was a different function. This is a square root function. So these are the input values. These are the values that are allowed. These are not rocks. The values that are not allowed are the values here in red. We can't have values that are bigger than 4, values that are smaller than negative 4. We can't have those because these are the regions that are negative. So this is every detail here for sign analysis, which is why this picture is extremely important for you. This is why this process is so important. It answers so many things. So here we have the graph, we have the domain and set notation, and sometimes they'll say, what does this answer in interval notation? In interval notation, just look at the graph. Interval notation is a modern notation that's a shorthand for this graph. So all I have to do is reproduce what you see here, but without any shading. And that's what you see over here. The shorthand of the graph. That's called interval notation. So here's our answers. This is how you answer 23, a domain question for when you have simply the square root. (25) f of x is the square root again, x squared plus 10x plus 24. Another square root function. Again, we set what's under the radical to be greater than or equal to 0. So we're going to say x squared plus 10x plus 24 must be greater than or equal to 0. Positive or equal to 0. So this is x squared plus 10x plus 24. We're going to have to solve this by sign analysis. This is number 25 here. And so we have to go through our sign analysis procedure, which means we focus on where it first equals 0. And then we'll focus on second where the quadratic is greater than 0. Because this portion means, again, greater than or equal to 0. Okay, so we're going to factor here. Now, without going through that technique like we've been going through, maybe you're really good at factoring. I hope you are, because after all this time, we spent so much time on factoring. We need a product that's equal to 24 and a sum that's equal to 10. So let's see if that's factorable. 6 times 4 is 24. And 6 plus 4 is 10. X plus 6 equals 0. Subtract your 6. We'll get x is negative 6. X plus 4 equals 0. Subtract your 4, and we'll get x is negative 4. These are the equalities. This is where my quadratic equals 0. So we're going to go up here again and now find where this is going to be positive. So we label negative 4, or actually it's the other way around. Negative 6, negative 4 here. Larger numbers are to the right. So this is where my quadratic equals 0, so I label that equal to 0. Now this partitions the real number line again into 3 regions. 1, 2, 3. So again here we need test points. A number to the left of negative 6, like maybe negative 8 works. A number between negative 6 and negative 4, negative 5 will work as a test point. And a number bigger than negative 4, region 3, will use 0 since it's available. Now we're going to test again the product here, because we're really testing where this equals 0 here, or where this is actually positive now. We're really testing this portion. I'm going to use the product, the factored form, because that's the easiest to actually evaluate in terms of sign. X plus 6 times x plus 4. So we're going to evaluate this factored version so people will understand that. We plug in the test points here. So my first test point of negative 8, we plug in for x. We end up with negative 2 times, looks like negative 4. So a negative times a negative gives us a positive. So region 1 will be positive. We're now going to test negative 5. So let's do the arithmetic. Negative 5 plus 6 is positive 1. Negative 5 plus 4 is negative 1. So I get a positive times a negative, which gives me a what? A negative. Test 0 now. 0, 0. So 0 plus 6 is 6. 0 plus 4 is 4, and 6 plus 4 is a positive value. That's going to be a plus. So region 3 is positive. So go back again and remember here. We're trying to find where this quadratic is, again, greater than 0, which means positive. And that happens, let's see, what did we do before? Let's take a look at that. It's positive in region 1, region 3, which means we're going to shade here the values to the left of -6 and the values to the right of -4, because this is where my region is positive, greater than 0. We also include the value of -6 and -4 because this is where it also equals 0. So we're going to include those. But we're going to draw this over a nice, fresh, real number here. I should say a real number line. So we're going to draw a real number line here. We say numbers to the left of -6 are shaded. Numbers to the right of -4 are shaded. Brackets because we include where it equals 0. Now this is the graph. If we want to describe set notation, we describe the left piece. This is numbers less than or equal to -6. Numbers greater than or equal to -4. Now this portion here is my description. Notice I use the word or. And so I can say the domain is a set of all real numbers x such that this description is satisfied. Now in terms of interval notation again, look at the graph. The graph tells you what your interval notation will be. The left piece is -infinity up to -6. We include -6. The right piece is -4 all the way to positive infinity, and we include the -4. The word or, we can use union, so we're saying unite these two interval pieces, and we find that simply by looking again at our graph here. So this is my left portion. This is the left portion. Here's the right portion. Here's the right portion, and again, we're saying just unite them or consider them together on the same real number line or on the same solution. And this is how we write the graph, the domain, which is in set notation, and interval notation. So I can go back and remove we removed too much. So here's how you'd see your answers. Now this is question number 25. '27 is similar. Square root x squared minus x minus 20. Since it's a square root function, set what's under the radical to be greater than or equal to 0. That has to be positive or equal to 0. So remember, we have to find the equality, and we have to find where it's positive. So I go straight to this procedure of solving, hopefully by factoring again. Now again, at this point, you could use your factoring technique. And I think -5 and +4 will work. You guys can double check that. Zero product rule says x minus 5 is 0, x plus 4 is 0. Add 5 to both sides, subtract 4 to both sides, we get x is 5, we'll get x is -4. These are the two solutions here. So this is where the quadratic equals 0. So again, we use this to label the real number line where the quadratic equals 0. Region 1, region 2, region 3. We need test points. Any number to the left of -4, like maybe -10, that's a test point. Any number between -4 and 5 for region 2, 0 is available, that's a test point. Any number to the right of 5, like maybe +10, is another test point for region 3. We're going to test our regions. Again, this is your real number line here. So I always advise to simply use, since we have to test the quadratic For signs, I always advise to use the factored format. Let's go back. Use that factored format, the product here. So let's test -10. This is my first test point. So we're going to test that, and our arithmetic becomes -10 minus 5, which is -15, -10 plus 4, which is -6, and a negative times a negative gives us a positive region, positive answer. So region 1 is positive. So you repeat the process now with the different test point for region 2. You repeat it with the 0 now, because that's your test point. So by arithmetic, we get 0 minus 5, which is -5, and 0 plus 4, which is +4, and a negative times a positive gives us a negative. So we get to repeat the process now again with a different test point. So we know region 2 is negative. Let's test region 3. This time, the test point is going to be +10. We get the test point here. And remember, those are your choices here. You just have to make sure you're within the proper regions. So by arithmetic, 10 minus 5 is 5, and 10 plus 4 is 14. A positive times a positive gives you a positive answer here. So we want to know where this is greater than or equal to 0. So what we can see here, being greater than 0 means being positive. So every number to the left here, let's undo that. These are the regions where it's positive. Region 1, region 3. So every number to the left of -4 here gives us a positive answer. Any number to the right of 5 gives us a positive answer. Now we include -4 and +5 because we include where this equals 0 as well. So you're really looking at your graph. So just draw a nice clean real number line for your domain. Numbers to the left of -4, we shade. Numbers to the right of +5, we shade. And use your brackets. That's the graph. Remember, if they want set notation, this left portion is less than or equal to 4. The right portion is greater than or equal to 5. And so in terms of the domain, we say the set of all x such that these two are satisfied, and we use the word or here. We just unite the left piece with the right piece together on the real number line. And again, in terms of interval notation, you're looking at the interval notation again, -infinity up to -4, include -4. Unite it with 5 to infinity, and here's your interval notation for your domain here. Now these are all domains of very special functions. These are the ones we really want to consider. These are the ones that will have some work to do. So we go down to 29 here. 29, our function is square root 2x squared minus 7x minus 15 here. Again, we set what's under the radical to be greater than or equal to 0. So 2x squared minus 7x minus 15 is greater than or equal to 0. This is 29. So at this point again, by sign analysis, we want to factor the equality here, or solve the equality, right? 2x squared minus 7x minus 15. Here's the equality. We want to factor this. So if we go into the detail of our procedure again, remember A times C, that's 2 times -15 will give you -30. That's our product. our sum here has to be -7. Our sum here is going to be this b value here. Now, if we did this already, 2x squared minus 7x minus 15, if we go back and look, looks like we haven't, well, looks like it was on number 29. Looks like we haven't done that one yet. It does look familiar, but okay, maybe not so familiar. We need two numbers multiplied together whose -30, but when added is -7. So, what are the numbers? Okay, -30, we can say 2 times 15, 3 times 10. So it looks like a 3 and a 10 gets pretty close to us. Remember, 3 times 10 is 30. One of them has to be negative. The 10 has to be negative. Positive times a negative will be negative. Now 3 plus -10 is -7. So these are the numbers here. So when we factor here, we'll get x plus 3, x minus 10. That's going to equal 0. Don't forget this important step here. The a value here is 2. So remember, since a is 2, we divide both of these numbers by 2 and look for where you get a whole number or an integer solution. Now 3 over 2 is not a whole number, so that means we write this as 2x plus 3. That means you move the 2 in front of this x. That doesn't happen for the next term. We get x minus 5 because 10 divided by 2 is that 5. Now this equals 0. So here's the equation we have to solve. So by the zero product rule now, we get 2x plus 3 equals 0. We get x minus 5 equals 0. And now we have two equations. Subtract the 3, and you'll get 2x is -3. Divide by 2, and you get x is -3/2. Add your 5 for the next equation, and you get x is +5. So this is where the quadratic equals 0. Go back now and let's use this information for sign analysis. Draw this real number line again. So we now get -3/2 and +5 here. So get -3/2, +5 here. This is where your quadratic equals 0. So we label this region 1, region 2, region 3. So we need test points in each region. Region 1, we need a number to the left of -3/2, which is -1.5. A -2 will work as a test point. We need a number in region 2 between -3/2 and 5. 0 is a test point, and we need a number to the right of 5, like maybe 10 again, but we can use 6 as a test point. And again, use the factored form. Test 2x plus 3 times x minus 5. You factored, use that to test the signs in sign analysis. Okay, so the first value we use again as a test point is -2. Plug in -2 here. So get 2 times -2 is -4. -4 plus 3 is -1. I get -2 minus 5 is -7, and a negative times a negative gives us again a positive. So region 1 here is positive. You're now going to test 0 here. So when you plug in that 0 now, you get 2 times 0, which is 0, plus 3 gives you 3. 0 minus 5 is actually -5. So a positive times a negative here gives you a negative region. We're now going to test +10. So when I test +10, 2 times 10 is 20, plus 3 gives you 23. 10 minus 5 is 5, so a positive times a positive gives me a nice positive region here. So this is here, sign analysis. We want to know where this is greater than 0 or equal to 0. It's greater than 0 in region 1, region 3. So we're going to shade numbers to the left of negative 3 halves. We're going to shade numbers to the right of 5. We're going to include negative 3 halves because that's where it equals 0. We're going to include positive 5 because that's where it equals 0, because we want to know where this is greater than or equal to 0. So we're looking at the answer. So we just have to now describe this in terms of a very fresh real number line. So negative 3 halves, positive 5, shade everything to the left of these values and to the right. Since it includes 0, we put a square bracket here. So this is the graph. This describes numbers that are, if we go back over here, let's look at this. Numbers that are less than or equal to negative 3 halves, or numbers that are greater than or equal to positive 5. X such that this gives me my domain. Looks like, there we go. Here's our domain here. Interval notation again. Just look at the graph. Negative infinity up to negative 3 halves. Close that. Union. 5 up to infinity. Here's my interval notation. So I got my set notation, my graph, and my interval notation. And this is 29. So this is sign analysis and why we learned it and why it's so important, and how it answers some questions here about domain of some very kind of exotic functions. The interesting functions here that we have to consider. So number 31 here, we get 3x squared plus 23x plus 14 here. Again, we're going to set what's under our radical to be greater than or equal to 0 here. $3x squared plus 23x plus 14 is greater than or equal to 0. And we're going to factor now. So don't forget, we needed a product to be 3 times 4, which will be 42. We need the sum to be 23. 3 times 14 is the product. Our sum here is 23. So two numbers multiply together, which is positive 42, but when added is 21. Looks like it'll be 22 times 1. Or I should say, well, that doesn't work. Let's double check. 3 times 14 here is 42. Sum is 23. So let's try to find a pair that multiplies. 1 times 42 doesn't work. 2 times 21 looks like it works. 2 times 21 is 42, and 2 plus 21 is 23. These are the numbers here. So x plus 2 times x plus 21 will be greater than or equal to 0. Now let's just write it this way. We're going to solve the equality, since that's our first step anyway. So remember, we're trying to solve this equality. Part of our sign analysis procedure. Do that first, because this means greater than or equal to 0. So do the equality. And don't forget, you have a here. Should say a here is 3, right up here, or over here. So we're going to have to divide by 3, and hopefully we get a nice whole number. But if we don't, that's okay. Like in the first case, we don't get 2 divided by 3 being a whole number, so we're going to have to move that 3 over here. The second case, we do get a whole number, x plus 7, so that equals 0. So we're solving the equality, so we set 3x plus 2 equal to 0, x plus 7 equal to 0. Subtract your 2, we get 3x is negative 2, divide by 3, and we end up getting x is negative 2/3. Here's my first solution. Subtract 7, and we get x is negative 7 here. So we're going to put this on our real number line here. Let's go back. Negative 7, negative 2/3. So negative 7 is smaller than negative 2/3. This is where that product is 0. 1, 2, 3. 3 regions. We need a test point now. Test point for every region. Negative 8, test point. A number between negative 7 and negative 2/3, negative 5 is available. And a number in region 3, 0 is available. These are my test points. Always use the factored form. Oops. X plus 2, x plus 7. Test the product. You're going to test the product for its sign now. So using negative 8 for x, let's do some arithmetic. We get 3 times 8, negative 8 is negative 24, plus 2, negative 22. Negative 8 plus 7 is negative 1. So a negative times a negative is a positive. Good. Plug in negative 5. So we're going to plug in negative 5 here for x. 3 times negative 5 is negative 15, plus 2 gives you negative 13. Negative 5 plus 7 is positive 2, and a negative times a positive gives you again here a negative here. Region 2 is negative. We're going to test region 3 using 0. 3 times 2 is 0 plus 2 gives you a 2. 0 plus 7 is 7. A positive times a positive means region 3 is in fact positive here. So ladies and gentlemen, we want to find where this is greater than 0, which is positive. And again, we see region 1, region 3. So that means we're going to shade and graph region 1, region 3. We're going to include where it equals 0. And you're looking at the shaded graph. Or you're looking at the graph, whatever is shaded here. So we want to make a nice clean kind of portion here for the solution. Let's draw a nice real number line here. So we know numbers to the left of 7. Numbers to the right of 2/3. We include negative 7. We include negative 2/3. This goes on forever. That's the graph of the domain. The left piece is numbers less than or equal to negative 7, or numbers greater than or equal to negative 2/3. Set of all x such that this is our domain. Negative infinity up to negative 7, union, negative 2/3 to infinity. Here's our interval notation. So there you go. This is number 31. Number 33. Number 33, we're at another milestone here. 33 is a combination of the two questions we asked here today. The two exotic functions, the square root function and the rational function, because technically this is not rational because the denominator is not a polynomial, but it's rational-like, meaning it behaves the same way. So we have two criteria to consider. Number one, I'm going to say here that the radical here could never be 0. So let's write this down here. This radical, x squared minus 16, could not be 0. I also know what's under the radical here. Let's write this in red. I know that x squared minus 16 has to be positive, greater than or equal to 0, I should say. So it's under your radical has to be greater than or equal to 0. We've been working with that already, but we have to throw out the condition where the radical, or x squared minus 16, equals 0. Here's the point. When you see here the radical in a denominator, what changes now here is what's under that radical here, the x squared minus 16, this is what you're going to do. Let's pick this color, I guess. X squared minus 16 now, what's under here, we set to be simply greater than 0. What that means is it has to be strictly positive, because when you take the square root of a positive, you get a positive, but it's not 0 and it's not negative. Positive numbers are neither. So this radical has to be positive. You have to throw out over here where it equals 0, because you can't have the radical equal to 0, which means you can't have what's under the radical equal to 0. So to make this sort of a very easy thing for you to remember here, let's go back. If you ever have a situation where you have 1 over the square root, if you have this, then when you're looking for the domain, set what's under the radical to be strictly positive. And you're going to solve for x. So this is for domain questions. And that's exactly what we did. So if we take the color away of being gray now, maybe, and let's focus on this and say, okay, we have x squared minus 16. It's under a radical, and it's in a denominator. It's in both positions. We automatically say, okay, x squared minus 16 must be strictly positive, and it can't be allowed to be 0. So we now use sign analysis here again and find where x squared minus 16 here is strictly positive. And so this is, again, excuse me, is a sign analysis procedure like we've seen in class. Even though you don't care about the equality, you still have to solve the equality for the procedure. So we're going to solve the equality here. Even though we're not going to use it like we did before. And solving the equality, remember, this is x plus 4. X minus 4 is 0. 0 product rule. X plus 4 is 0. X minus 4 is 0. You get to subtract your 4, and we'll get x is negative 4. Add your 4, we get x is positive 4 here. So here's our solutions for sign analysis here. Let's take a look at how this is really going to work now. Let's be careful here. In the past, you located negative 4 and positive 4, and in the past, you did the following. You said, okay, at these values, our quadratic equals 0. Now, it certainly does because we just solved the quadratic. But we're looking at here, the quadratic is in the denominator now. So for the fraction, The fraction now will be undefined at those values, because if we plug in those values for x, we'll get 1 over the square root of 0, which is 1 over 0, which is undefined. So those values of x make our denominator equal to 0, even if you have a square root, because the square root of 0 is 0. So we label this as undefined now, and that's the difference. So this is what you need to remember here. This is what you'll be tested on, and we now have to determine the sign of each region here. So the value to the left of -4, we can use -5 as a test point. 0 is available, and 6 is available as a test point. And the procedure is the same. And so we're going to test again the product here, which is x plus 4 times x minus 4. So let's test this. The test point of -5 here, we plug in and do arithmetic. So -5 plus 4 is -1. -5 times minus 4 is -9, and a negative times a negative gives us a nice positive region here for 1. We're going to now test region 2 using the test point of 0. 0, 0, 0 plus 4 is 4. 0 times -4 is -4. Positive times a negative gives us again a negative. We're now going to test region 3. Positive 6. 6 plus 4 is 10. 6 minus 4 is 2. Positive times a positive gives you a positive answer. So again, this is our sign analysis. We're looking for where the product is strictly positive now, because this is where it's greater than 0, meaning positive. Region 1, region 3. So now the values of x that give you a positive product are the values to the left of -4 and the values to the right of positive 4. Now here's where the difference is. Because -4 and positive 4 here give us an undefined fraction, meaning we have rocks at those values again. What that means here is just shade whatever is shaded as your answer here. So when I draw my real number line, I know only numbers strictly to the left of -4, I got to put a parentheses. That means don't include -4. If I did that, I get a fraction that's undefined. Positive 4, shade numbers to the right. And again, use a parentheses, because if I use 4, I get a fraction again up here that will be undefined. This is what we're talking about. We can't have that. So you're looking at the domain. It's simply region 1, region 3, without the endpoints of -4 and positive 4, because it's undefined. So here's the graph of the solution, and if they ask for the set notation, numbers less than -4 or numbers greater than 4, formally in set notation, so the real number is x, such that x satisfies this requirement. Interval notation is the same as before. -infinity up to -4, union 4 up to infinity. So here you go. So here's how we handle number 33. So we have to be careful with that. Let's see how number 35 behaves. 35, the function here is going to be 1 over square root x squared minus x minus 30. And again, in this case here, we have to set what's under the radical not to be greater than or equal to 0. We have to set it to be strictly positive, because it can't be 0. If it were 0, we're going to get an undefined fraction again. So for sign analysis, let me write that down. Let's use our sign analysis procedure. We want to know where this is strictly positive again. We're going to have to factor, or we solve the equality first. And when we solve that equality, we're going to factor. So notice when you factor, you should get the following. -6 plus 5. Zero product rule now. Zero product rule says, we'll put it down here, x minus 6 is 0, x plus 5 is 0. Add your 6, we get x is 6. Subtract your 5, we get x is -5. So we get -5, +6. So remember, this is where it's equal to 0, but it's in the denominator position, so we label undefined here. That means your whole fraction is undefined. And that partitions our region again into 3 portions again. 1, 2, and 3. So you need a test point here, like -7, 0, 10. These are good test points. And again, you always test the factored form. This form here. We're going to look at the sign. We want to know where that is going to be strictly positive, greater than 0 here. So let's do our arithmetic now. All right, we're going to test -7 as a test point here. So plug in -7. We get -7 minus 6 will be -13. -7 plus 5 is -2. A negative times a negative gives us a nice positive region. You're going to test again. 0. Plug in 0 for x, and we get -6, +5. Negative times a positive gives us a negative region. You're now going to test again. 10. 10 minus 6 is 4. 10 plus 5 is 15. A positive times a positive gives us again here, for testing 10, it will give us a, let's double check, positive region here. So all these test points here have to be tested. Notice again, we want to find where this is positive. So positive happens in region 1, region 3. It happens for the values of x that are to the left of -5 and to the right of 6. We don't include the endpoints of -5 and 6 again because that's where this fraction here is undefined. Those are rocks. So we're going to sketch a nice real number here, real number line. We're going to shade things where we should. I'm going to describe the domain. This is numbers to the left of -5. Shade that. Numbers to the right of 6. We're going to shade this. Again, we do not include the endpoints, because if we did, the fraction will be undefined here. Those values, again, give us 1 over the square root of 0, which is 1 over 0, which again is undefined if I were to use the -5 and the +6 value. So remember, here's the graph. This is numbers to the left of -5, numbers to the right of 6. So they can ask us in set notation, set of all x, for the domain here. Here's the set notation answer. Interval notation, -infinity up to -5, and 6 up to infinity here. So here's how we answer the question here for the domain for number 35. Number 37. Function 1 over the square root of 2x squared minus 7x minus 15. Again, this time, since you still have a square root function and it's in the denominator position, we're going to set this here equal to, or I should say, this has to be strictly positive. It could never be 0. If it were 0, we're going to have 1 over the square root of 0, which is 1 over 0, which is undefined. So we can't have the denominator ever be 0. So by our procedure for sign analysis again, we're going to have to solve the equality, which is 2x squared minus 7x minus 15 equal to 0. Again, you factor. So by that factoring procedure, don't forget, the product has to be negative 30, and the sum is negative 7. So 2 times negative 15 is negative 30. That's what we're looking for. And that sum is negative 7 here. So here's the sum. Here's your product. We need two numbers. And so 10 and 3 give us 30. If the 10 is negative, that's negative 30. Negative 10 plus 3 is negative 7. So here are the numbers. So we're going to solve the equality here. X minus 10, x plus 3. So don't forget though, we have an a value equal to 2. So I'm going to have to divide by 2 here. So 10 divided by 2 is going to be 5. So we have x minus 5. And then we get 2x plus 3 here. This 2 here, since you don't get a whole number again, we move it up. And again, you should double check here to make sure that when you multiply, you do get the quadratic. Looks like we do. So by the zero product rule again, you solve both of these equations. Set x minus 5 equal to 0, and 2x plus 3 equal to 0. So I can add 5 to both sides, and I'll get x is 5. Here's one solution. Subtract 3, I'll get 2x is negative 3. Divide by 2, I'll get x is negative 3/2. Okay. This partitions our real number line into 3 regions. Negative 3/2 and positive 5. But don't forget, this time, even though we set that equal to 0 and solve for x, as a fraction, this is the location where your fraction is undefined. The denominator will be 0. So this will define 3 regions again for us, where we need some test points. Any number to the left of negative 3/2, like negative 4, we can use as a test point. 0 is available, and then 10 is available. So like I've said before, always test the product, the factored form, because that will make everything a lot easier. Test the factored form. We're trying to find where this is going to be strictly positive. So we only care where it's positive now. So test negative 4 here, and when you do, you get negative 9 times negative 8 plus 3 is negative 5, and a negative times a negative gives you a nice positive region. We're going to test 0 now. Use the 0 for a test point now. See what your arithmetic is. 0 minus 5, that's negative 5 times 3. So a negative times a positive gives you again a what? Negative region. So you're now going to test 10, plug in that 10. Ten minus 5 gives you 5. 2 times 10 plus 3 is actually 23. So I don't care about the answer, just the sign. Positive times a positive is a positive again. So we found where, or we should say we find which regions are positive. And we can see that region 1 is positive, region 3 is positive. So we're going to shade numbers to the left of negative 3/2, numbers to the right of 5. So maybe we should put it all down here, since we're running out of space. Numbers to the left of 3 halves, numbers to the right of 5. So we're going to shade everything to the left, everything to the right. Notice, again, we do not include these numbers. This is what I'm focusing on here. We don't include negative 3 halves. We don't include 5 because that's where this is undefined. So get rid of that stuff. Okay. What they really are saying, or what you really do, is put a parentheses as opposed to a bracket. Here's my graph. So these are numbers here that are in my domain. Let's describe them as sets here. Numbers to the left of negative 3 halves, numbers to the right of 5. This is OR, set of all x, such that this is my domain here. If you want interval notation, negative infinity up to negative 3 halves, union 5 up to infinity. So here's my interval notation. So as you guys can see, this comes down to the one technique here that I keep preaching about for you. Sign analysis, and that answers a lot of questions. It's a good technique. It's found in mathematics for a lot of context, a lot of problems in your future. So I focus on some very special kind of questions where you'd simply use sign analysis. 1 over square root 9 minus x squared. And as we've seen in class, this isn't the only situation where you find the domain and then later the range, but this is kind of where we started. That was built on sign analysis and actually solving equations, quadratics, and beginning and intermediate algebra. So, okay, we're going to use sign analysis again for the last question. That 9 minus x squared has to be strictly positive. We can't allow it to be 0 because that gives us 1 over the square root of 0, which will be 1 over 0, which will be undefined. So we can't allow that to be 0. Sign analysis procedure requires us to find where this equals 0. So we'll factor. That's a difference of perfect squares. Zero product rule says this is 3 minus x, which is 0. 3 plus x, which is 0. I can add x to both sides. I'll get 3 as x, or x is 3. I could subtract 3, and I'll get x is negative 3. So in my sign analysis procedure here again, I found at negative 3 and at positive 3, the fraction will be undefined because my polynomial is in the denominator here. So I now get again region 1, region 2, region 3. Test points. Any number to the left of negative 3, like negative 5 or negative 4. Zeros between negative 3 and positive 3, it's available. Positive 4 is to the right of 3, so I have some test points. And again, I always use the factored form. 3 minus x, 3 plus x. I always use this factored version here. So we're going to test negative 5 here. We're going to plug in negative 5. Oops. Let's see what we get here. Just be careful. Yeah. Let's put the negative 5 by the x. So let's really take a close look now. 3 minus a minus makes this 3 plus 5, and then 3 minus 5. So I get 8 times negative 2 here. So be very careful with your arithmetic with this question. Positive times a negative now gives us a negative region 1. So this is the first time you might have seen that kind of thing after a lot of these questions. We had a few that were this way. So it's not always a pattern of positive, negative, positive. You might find negative, positive, negative. So be careful. Go through the procedure. So when I test now a 0 here, let's see what we get. 0 as our test point. Plug in 0. And then 3 minus 0 is 3. 3 plus 0 is 3. So a positive times a positive gives us a nice what? Positive region. So we have to test those values. Test 4. Plug in a 4 now. So our arithmetic becomes 3 minus 4, which is -1, and then 3 plus 4, which is 7. So I have a negative times a positive, gives me a negative. So region 3 is negative. So be careful with your sign analysis. Now go back. We want where this product here is positive, greater than 0. Region 2 is your positive region. Now remember, we can't have it equal to 0, so we don't include the -3 or the +3 in our answer. So what I'm going to say here is, let's go back. Region 2 is positive. We're only going to shade numbers between -3 and +3, and we don't include the endpoints of -3 and +3. So the graph looks like the following here. Just shade numbers between -3 and +3. Use your parentheses. And if they want set notation, don't forget, this is where all the x values are. You're talking between. -3 will be less than x, which is less than 3. Don't use your equality because it can't equal 3. This is going to be our description for set notation for the domain. And finally, your interval notation is going to look like -3 up to 3 simply by looking at your graph, doing the shorthand. So this is how we find the domain here of various functions that we looked over in class, and this is part of some of your homework questions. So here's the solutions. So I hope it helps.